This is going to be our first video into process known as linear programming, which is going to be an application to systems of inequalities, okay? Um, so let's consider the following system and its solution, okay? So first of all, the system itself has three inequalities. These are going to be considered the constraints of the system, okay? And you can see over on the right-hand side, I have those three constraints graphed, and then their overlap is the green shaded region, that triangular region. This is known as the feasible region, okay? So what we're doing in linear programming is we're trying to maximize or minimize a function over a given region, okay? And here's the absolute most crucial idea of all of this. The maximum or minimum value that we're trying to find for our related function, it always occurs at a vertex of the feasible region. So for this particular region graphed, we would want to be focusing on the three vertices of that triangle, okay? You would take those vertices, plug them into your objective function, and then see what gives you, which gives you a high value and which gives you a low value, okay? So let's get right into a complete example of this. All right, notice directions. We have to graph the system of inequalities, name the coordinates of the vertices of the feasible region, and then find the maximum and minimum values of the function for this region. Okay, so let's focus on graphing the constraints of the system first. Okay, starting with x is less than or equal to 2. That's going to be a vertical boundary line at x equals 2. And for that, I would be shading to the left of it where all points are going to have x coordinates smaller than 2. Okay, I'm not actually going to do the shading right now, though, because it'll get a little busy. Next inequality or next constraint is y less than or equal to 3. That would have a horizontal boundary line, and I would be shading below that. And then finally, the last constraint, it has a y-intercept of 3, slope of -1. Okay. And if I do a test point of the origin for that, I'd end up with 0 is greater than or equal to 3, which is false. So for that last line that was just drawn, I would have to shade the half plane that doesn't have the origin in it, which would be above that line. So you take all three of your shadings into consideration, and you end up with this triangular region as your feasible region. Okay, so once you have the shading done and you identify the feasible region, now you're focusing in on the vertices of that region. Okay, there are three vertices. Let's list them out as ordered pairs. The first is the point of 0, 3. Then you have 2, 3. And then you have 2, 1. Okay. All right, now once we have those vertices, now we bring the objective function into play, okay, which is of course listed right here. And notice the makeup of that function. We have f of x, y is equal to 2x plus y. So this is your first taste of the notation f of x, y. Understand that that's just another notation to represent z. Okay, so what that tells me is that this objective function is really representing a plane in coordinate space. Okay, so we're kind of working in both 2 dimensions, which is what you see on the screen right now for the feasible region, but then we have this objective function which correlates to coordinate space. Okay, what we need to do is take each point from our feasible region, each vertex, plug it into the objective function to see which points give us the highest z value and which one gives us the lowest z value. Okay, so I'm going to turn this into a table. where the left side of the table represents the ordered pair xy, the right side represents the z value given from the objective function by that ordered pair, okay? So if I were to plug 0 in for x and 0 in for y into that objective function, that would lead me to 2 times 0 plus 3, which results in 3, okay? If I plug in 2, 3, that's going to lead me to 7. And then if I plug in 2, 1, that's going to lead me to 5. Okay, so once I get those three z values, I want to pick out the largest value, which in this case is 7. That's my max value. And then the smallest value, which is my minimum. Okay, and here's how we're going to write our answer. We're going to say we have a maximum value of 7 at the point 2, 3. And then similarly, we have a minimum value of 3 at the point 2, 3, or I'm sorry, 0, 3. Okay, and together those give us our answer to this particular problem. All right, so I've walked you through the procedure behind this whole process. Now let's give you a better conceptual understanding of what it is we're doing when we're working in both 2D and 3D here. Okay, so I have a nice GeoGebra applet to hopefully illustrate this for us. Okay, and I'm gonna mess around with this a little bit. I'm going to move my vertices in this region so I can try to make it. Okay, so right there we're close to the region that we were working with in our example. Okay, and then I'm going to make this have the exact same plane as we were working with. Okay, so you can see at the right hand side of the screen we have the 2D feasible region, and then over on the left hand side we're in coordinate space, and coordinate space is showing two things right now. It's showing the plane represented by that objective function, so that plane is in gray there. Okay, let's kind of rotate around a couple different ways. You can see how the plane's positioned, and then you can see that the feasible region that's shown over on the right is also showing up on the left-hand side. It's kind of like below the plane right now. Okay, so what we're doing in this process of linear programming is we are projecting up that 2D feasible region into coordinate space so that it intersects our objective function's plane. Okay, so there you can see the green region is the intersection of my feasible region once it's projected up into the plane here. Okay, and then you can see there's a blue point within the feasible region. I'm going to project that up as well, and it's going to correspond to a point within that intersection with the plane. And now that I'm bringing it up into coordinate space, it's now going to have a z value associated with it. So that's the point that you would see in yellow on your screen in the left. And we can move this point anywhere within the feasible region. And what we want to notice is that the lowest point that we can possibly get for this feasible region takes place at that vertex at 3, 0. And then the highest point takes place at this vertex of 2, 3. okay? We can't get a lower high point in the middle of the feasible region. It has to take place at a vertex, okay? So hopefully that gives you a really good illustration of exactly what we're doing here in this process of linear programming. All right, let's go back and get a second example taken care of. So similar process, we've got three constraints. We have an objective function. We're trying to maximize and minimize that function using the feasible region from the constraints, okay? So let's start with the first constraint. It's in standard form, so I'll use the x and y intercepts. X-intercept is -2, y-intercept is 1, and I'll just get a couple more points based off the slope there. Okay, so there's the first boundary line. For shading, if I plug the origin in for that, I would end up with 0 is less than or equal to 2, which is true. So for that boundary line, I would be shading below. Okay, keep that in mind. Middle constraint, x-intercept is at 4, y-intercept is at -2. Notice this ends up being parallel to the other boundary line. Okay, shading for that, use the test point of the origin again. You'll end up with 0 is less than or equal to 4, which is another true statement. So for that boundary line, you would be shading above. So right now, the two shadings would overlap in between the two parallel boundary lines. Okay. Lastly, x-intercept, final constraint has an x-intercept of -2 and a y-intercept of -2. So use those to find some more points. There's your final boundary line. Origin for the test point is going to lead me to 0 is greater than or equal to -2. That is also true, so I would be shading above that final boundary line. And putting all three shadings together, my feasible region, the overlap would be in here. Okay. And what I want you to notice is that that region, it's not closed over in the upper right-hand corner there. So we're going to refer to this as an unbounded region. Meaning it continues, upward and to the right. Okay. So based off of that, there only are two vertices to this region. Okay, let's list those out. I'll start it in a table here. So they are 0, -2, as well as -2, 0. Okay, so we'll plug each one of those into our objective function. Plugging 0, -2 in is going to lead me to -6 for z. Plugging -2, 0 in is going to lead me to -4 for z. So since there were only two vertices, it stands to reason that the smaller z value of -6 would have to be my minimum, and then the larger z value of -4 would have to be my maximum, right? Well, that is not the case. Since this region is unbounded, you're never going to have both a you're not going to have both a maximum and a minimum. It's typically going to be one or the other. Okay. Now, the only way we can figure this out without like graphing everything in an algebraic manner would be using a test point from the feasible region. Okay. So just pick a random point somewhere in your feasible region. I'm going to use 2, 0, which is right here. So I'm adding a third point in. Make sure we designate this as our test point. Okay. And we're going off the idea, if we go back a couple slides here, that your max or your min value of your objective function should always occur at a vertex of the feasible region, right? So this test point of 2, 0, it's not a vertex. when I plug it in, I'm going to see if the corresponding z value is larger than both of the z's of the vertices or smaller than both of them, okay? That's going to help me conclude, do I have a max or do I have a min in this scenario? So if I plug 2, 0 in, it leads me to positive 4, okay? Now positive 4 is larger than either z value given by the vertices, so I can conclude there's no maximum in this situation, okay? Let's write that down so that we have a clear understanding here. So we're going to say, since 4 is larger than the result from the two vertices, we can conclude this function has no maximum value over the feasible region. Okay. And if there's no maximum, then that means there should be a minimum. So out of the two z values from the vertices, pick out the smaller one, -6, and there's my minimum. Okay. So I will say I have a minimum of -6 at the point 0, -2. All right, and there you have it. Okay. So now it's your opportunity to practice. When you click over to the next page or next tab, you're going to see I already have a feasible region graphed for you. So the constraints have been taken care of. All you need to do is use the objective function that's given to you, try to maximize it and minimize it using the vertices of the graphed feasible region. Okay, so take a moment to work through that yourself as you pause the video and then come back and check your work.